Hello all, this is the second lecture on the lecture series on moving loads and influence lines. This lecture deals with the problems involved in drawing influence line diagram. This comes under module 4 of structural analysis 1 of S4 BTech civil engineering students. Consider the first problem. A single concentrated load of 5 kN crosses a girder of 10 meter span, simply supported at its ends. Using influence line, determine the maximum positive shear force, negative shear force and bending moment at a point C from the left end. So let us draw the figure. Span of L is given as 10 meters and C over here is given as 7 meters. And the load is 5 kilonewton. So we'll do it for 1 kilonewton and then we'll multiply with 5 to get the corresponding forces. So this is a shear force diagram for section C, and this is the bending moment diagram for the section C. So where will be the positive maximum shear force? Positive maximum shear force will be at the left of the section, immediately left to the section, which is equal to C by L. So that is equal to 7 by 10. C is 7 and L is 10, so 0.7 kilonewton. This is for 1 kilonewton force, so for 5 kilonewtons it will be 5 into 0.7, which is 3.5 kilonewtons. Now for negative shear force, maximum is just to the right of the section, so that is 1 minus C by L, which is 1 minus 7 by 10 is equal to 0.3 kilonewtons. So which, for 5 kilonewtons it will be 1.5 kilonewtons. For maximum bending moment at the section, the point load has to be kept immediately below the section, immediately on top of the section C. So bending moment is nothing but C into 1 minus C by L, that is equal to 7 into 1 minus 7 by 10 multiply by 5. You will be getting it as 10.5 kilonewton meters. For the above problem, determine the absolute bending moment. So this is the section, this is the figure for getting the moment at the section C. Now what we need is the absolute bending moment. So we have seen that the absolute bending moment will be where the section can be anywhere between 0 to L span, right? So how will you get the maximum bending moment? For that you have to differentiate the bending moment equation. So we have to differentiate the bending moment max equation, which is x into L minus x by L at any given section x. So you do that, you will get the x value of x is equal to L by 2. So what is so at x is equal to L by 2, you will be getting the maximum bending moment for the entire section. So absolute bending moment will be x into L minus x by L. So put x is equal to L by 2 there, you will be getting L by 4 which is for 1 kilonewton. So for 5 kilonewtons it will be WL by 4. So in this case it is W into 10 by 4, that is 12.5 kilonewton. So it happens at the mid span and that value is 12.5 kilonewton. That we have already seen using the bending moment diagram also. Let's consider another question. A uniformly distributed load of 2 kilonewton per meter and a length of 35 meter crosses a girder of 25 meter span, simply supported at its ends. Using influence lines, determine the maximum positive shear force, negative shear force and bending moment at a point 8 meters from the left end. So this is the case where the UDL is having a span which is more than the span of the member. So how will you get the maximum positive shear force? You just keep the entire UDL to the left of the section where you need to find out the maximum shear force, so that the head of the UDL is placed at the section. So it looks like this. So for the entire 8 meter span, so C is 8 meters here, so for the entire 8 meter span the UDL will be there and the value of UDL is 2 kilonewton per meter. The total span is 25 meters. So you know this is the shear force diagram. Please understand that the shear force diagram, the bending moment diagram, everything for a member simply supported beam is this, whether it be a UDL or a simply supported or a concentrated load, okay, or in any kind of loading, the influence line is going to be like this for shear force, and the other for bending moment, and for reactions also we have seen. You just have to see how to calculate the value of the shear force depending upon the type of loading, that is all, right? So when it was a concentrated load, you took directly the value of the you multiply the magnitude of the load with the ordinate immediately below that in the shear force diagram. Now when it is a UDL, you have to multiply the magnitude of the UDL with the area of the shear force diagram which is coming under that. That's the only difference. So what's the positive maximum shear force at C? That is equal to half base into altitude. Half into base is nothing but C. So C by 2 into altitude is C by L, right, for the blue shaded triangular portion, into W is the load. So W into C squared by 2L, which is 2.56 kilonewton. Now coming to the case 2, to get the negative maximum shear force at section C, the tail of the UDL should be placed at the section. So again the same shear force diagram. Now the area is the yellow shaded portion. So half into base is nothing but 25 minus 8, which is how much? 17, into altitude. Altitude is 1 minus C by L. So half into L minus C by 2 into 1 minus C by L, which is L minus C the whole squared by 2L, which you will get as 11.56 kilonewtons. Now the third case, to get the maximum bending moment, you have to place the load immediately below the load. For in the case of concentrator. So when it is a UDL, you have to keep the, when the span is length of the UDL is more than the length of the member, then you have to keep the entire UDL on the member to get the maximum bending moment, right? So that will be bending moment at the section C will be half base into altitude again. Here the base is the length itself, and altitude is C into L minus C by L, and C is 8 here. So 2 into 25 by 2 into 8 into 1 minus 8 by 25, which you will get as 136 kilonewton meters. Now for the above problem, to determine the absolute maximum bending moment, what should you do? The absolute maximum bending moment will be occurring at the center of the span when the entire span is loaded with UDL, because it is a simply supported beam, right, symmetric. So bending moment will be maximum there. So what will be that value? Substitute x is equal to L by 2 in the equation for bending moment max. So instead of C into L minus C by L, it is actually x into L minus x by L, and put x is equal to L by 2 in this equation. You will be getting it as WL squared by 8, and that value is 156.25 kilonewton meters. Let us consider another question. A uniformly distributed load of 3 kilonewton per meter and a length of 5 meters crosses a girder of span 25 meter, simply supported at its ends. Using influence line, determine the maximum positive shear force, negative shear force, and bending moment at a point 7 meters from the left end. So in this case, you can see that the UDL is having a length which is less than the span. Okay. So what is the condition for maximum positive shear force? The head of the UDL should be placed at that section. Okay, so you have C is equal to 7 meters, A is 5 meters. So the same shear force diagram. Now the shaded portion is only, it's a trapezium, right? And the trapezium, and at a section A, at that end, what will be the higher end of the trapezium is C by L, and the smaller end over here, it will be L minus C by, L by 2 minus C by L. Okay, so you just do that. So you will be getting W into shaded area. You know how to calculate the shaded area, which is the area of the trapezium, and you will be getting it as 2.7 kilonewtons. So in the second case, what's the case? That's a negative shear force. So for the negative shear force, again you have this shaded portion. The tail of the UDL should be placed at the section. So 1 minus C by L is the highest altitude. The other portion will be, since it is a distance of A, you can always calculate that using similar triangles. So 1 minus C by L minus A by 2 by L, A by 2L, that will be the total area, A into 1 minus C by L minus A by 2L. So you will be getting that value as 9.3 kilonewtons. Now in order to get the third case, which is the maximum bending moment. So you know, for the maximum bending moment, we have to keep the UDL at the section C in such a way that C1 by C2 is equal to C by L minus C. So C1 by C2 is equal to, what is C here? 7, and L is 25. So C 7 by 25 minus 7, which is 7 by 18. So you will be getting C1 is equal to 0.389 C2, or C1 minus 0.389 C2 is equal to 0. Let us take it as equation 1. Now we know C1 plus C2 is equal to 5, the total span of UDL. From these two equations, you will be getting the value of C1 as 3.6 meters and C2 as 1.4 meters. Now what about the bending moment equation? It is W into area under the influence line diagram, right? So this is the influence line diagram. So I have calculated these values. So you will be getting the two ends of the trapezium like this. So there are two trapeziums. The center portion is C into L minus C by L, and this end you will be getting it as X into L minus X by L, which you will get as 4.032, and the right end you will be getting again as 4.032. So you can always calculate using the equation for trapezium, half into base into sum of the altitudes, right, into 3 kilonewton per meter. So you will be getting the maximum bending moment as 68.04 kilonewton meters. Now if UDL of 4 kilonewton per meter and 8 meter length crosses a girder of span 40 meters from left to right. Using influence line, determine the value of shear force and bending moment at a point 15 meters from the left support when the head of the load is at 18 meters from the left support. Also find the support reaction. So here please understand, this is the case of UDL where the span or length of UDL is less than the span of the member. But here what is asked is, you are given the location of the UDL. Okay, you are given that the UDL is kept, the head of the UDL is kept at 18 meters, and you are asked to get the bending moment at section C when the UDL is kept like this. Okay, so you understood the difference. In the previous case, you are having the UDL that is moving, and at the section C, what is the maximum shear force, maximum bending moment, that is what we are finding. Now in this case, the UDL is kept at this position, and you are asked to get the bending moment on the shear force at the section C, and you are also asked to get the support reactions. So let us find the shear force first. So you are not asked to get the maximum positive or maximum negative, you are asked to get the shear force at the section, because there is no maximum positive or negative. The shear force, the member is like this, so you have to get the shear force at that section C. So how will you get the shear force? You draw the shear force diagram. Now under the shear force diagram, you have one portion in the positive shear force portion and the other in the negative shear force portion, right? This entire thing total added together is the shear force at the section C. So what is the shear force at the value of the positive shear force minus the value of the negative shear force, right? So you add up, you find out the area of the positive shear force and find out the area under the negative shear force diagram, and then deduct these two. So that is half into 5 into 0.25 plus 0.375. C by L is 0.375, and the other portion is X by L, and here X is nothing but 10 meters, because 15 minus 5, that is 10, divided by L, so it is 0.25. Similarly, so you will be getting that as 6.25 kilonewton. Now how will you get the maximum negative shear force? Half into 3, that is W into 3 is what? The base, right? 5 meters left to the C and section C, and 3 meters right to section C, because it is at 18 meters. The head is at 18 meters. So and section C is at 15 meters. So to the right it is 3 meters, right? So 3 into 0.625 is 1 minus C by L, and the other portion you can always calculate the same way. It will be 1 minus X by L, and X is 18, so 1 minus 18 by 40, which you will get as 0.55. So you will get the maximum negative shear force as 7.05. So what's the difference? 6.25 minus 7.05, it is minus 0.8 kilonewton is the shear force at section C. Now how will you get the bending moment at section C due to this particular load kept at a distance of 18 meters from the left support? You calculate the show the bending moment diagram and at the section C, and then take the trapezoidal area, right, and add up the entire thing. So this is how you will be getting it, right? There are two trapeziums. The center part is C into L minus C by L, you get as 9.375, and the left part will be, you will be getting it as x by L. L is that x is nothing but 15 minus 5 into 9.375 by 15. You just do take similar triangles on both the sides, you will be getting this values. Okay, and you will be getting it as 65.5 kilonewton meters. And you're asked to get the support reactions also when the load is here, right? So to get the support reaction, you know, for VB it is the upper triangle and VA it is the lower triangle, and you will be getting the value of VB as the blue shaded portion, right? And the value of VA will be the yellow shaded portion. So what is VA when the load is at C? It is half into base. Base is 8 meters, which is A, into 0.75 plus 0.55, which is, you will get as, which is for 1 kilonewton. So for 4 kilonewtons it will be 20.8 kilonewtons. And similarly for VB it is half into 8 into 0.25 plus 0.45, 2.8 kilonewton for 1 kilonewton load and kilonewton per meter load. So it is 11.2 kilonewtons.